Okay, so the H2SO4 deprotonates. What happens to the proton? So how it happens is the electron pair from the oxygen will pick up the proton from H2SO4, which is a strong acid. The protonated epoxide is similar to that bromonium ion there. We have a positive charge on a 3-membered ring species. Right? That positive charge is making it so that the electrons in this bond are, the bond itself is longer and weaker than the bond over on this side. So therefore, this is the side that an incoming nucleophile would attack. So if we just put, catalytic sulfuric acid in water, for example, when the water attacks, then as in the case with the bromonium, the water is going to attack the side that's more substituted because that's the side with the longer weaker bond. So then the epoxide breaks open. And when we look at the product, we're going to see that the OH and the new oxygen from water end up anti to each other in the product. So now if we just fill in the remaining pairs, kind of adjust their bond angles a bit. If this is attacking this side, then these two things are going to get pushed up, but they're going to keep their relationship being front or back, right? So this is going to go up, but the hydrogen is still pointing back, and the methyl group is still pointing out. So that's what the intermediate product would look like. So if you have another molecule of water, which is going to be a much stronger base than your hydrogen sulfate anions, water is the thing most likely to deprotonate here. So at the end of the day, after acid catalyzed hydration of an epoxide, you end up with an anti-diol. Let's just use something a bit more complicated. If I take that epoxide that we that we made earlier, treated it with sulfuric acid. And let's use sulfuric acid in the presence of ethanol. So we're using ethanol as the solvent for this reaction as well. Again, protonation of your epoxide oxygen. So when the thing that's going to be the nucleophile that attacks this now is your alcohol solvent. Which I'm just going to draw backwards. So the thing we want to note here, which was probably more obvious in this example, the way it was drawn, is that your nucleophile, wherever your epoxide oxygen is, the nucleophile has to attack from the opposite face, right? So if this is pointing up in the plane, then your nucleophile has to attack from below. With this one, if this epoxide ring is pointing up, then the ethanol acting as your nucleophile must attack from the back. Okay? So if that's attacking from the back, right? Then we know that the OH from the existing epoxide oxygen is going to end up pointing out. Your new bond to your ethanol must be opposite to this. So therefore you must have here that's the new bond made to the ethanol. So in doing that, this methyl group must have gotten pushed up, just in the same way that it got pushed up here. So your final product in this case would look like that. So just to kind of summarize a couple of things to do with this reaction. Right? The reaction has some facets that seem similar to an SN1 type of process. Stop.
No, something's blinking. I don't know what it is.
That means the tape is about to run out.